Okay, Chapter 4 continues the discussion about forces. It starts to focus more on some of the resistance forces. So most of it will be on friction, but we'll do a quick little discussion on air resistance here because it's a type of friction. So by the end of today, I'll be able to identify the part of the force of gravity plays in skydiving and with objects on a ramp, and we'll chat a little bit about some air resistance. There is a video link here, right here. Okay, so in the PDF on the website, you can download and click on it. It's a winged base jumping. It's pretty cool. Watch for the guy as he goes through the little canyon. Look for the balloons and watch for the shadows. As the shadows get really big, that means they're close to the ground. As the shadows get smaller, they're farther from the ground. It's pretty terrifying, but you might like it. And it'll give us some context to talk about skydiving. Okay, so we have two objects here that have been frozen with flash photography. So the one on the left we should recognize as accelerated motion. So you can see these separations between the water droplets is getting larger. Okay, and over here we have a seed from a tree falling, and you'll notice that these distances are actually about the same. And this seed, this is the seed pod right here, it has its own little wing. And that wing increases its surface area, which increases the air resistance on it, so it doesn't fall quite the same way as a water droplet without the wing would. Okay, and one of the reasons biologically would be the longer that seed is in the air, from our projectile motion discussion, the longer it's in the air, the farther it can travel horizontally from the parent tree. So this is one way to get seeds further from the parent tree and to have more trees growing in a larger area. Okay, so force of air resistance factors. If you've ever stuck your hand out the window when you're driving down the highway and you've sort of made a blade with your hand, you can feel air resistance very quickly. If you change the angle, it goes up and down. You can pretend you're an airplane. There's a couple of big ideas that have to come out of this, and this is big area equals big resistance. So if you opened your fingers, you would feel less force from the wind and the air hitting your hand than if you close your fingers. Okay, so faster moving equals bigger resistance. So obviously if you're driving on the highway, you're really going to feel it. If you try this in town, you won't notice it as much. So, and this second one here is really the one that makes this not a grade 11 topic. So this is what we call a feedback loop. So the faster the moving the object is, the bigger the resistance force, the air resistance force will be on it. So what happens though is that as that force gets larger, the object speed changes because now we're accelerating at a different rate. So now the speed changes, which leads to a change in the force of resistance, and it just keeps going in this big cycle like this. And mathematically it starts to get a bit overwhelming. So mostly we're interested in just the concept that air resistance affects the forces that are on an object, especially on a skydiver, and that's when we're going to spend a little bit of time talking. So the flight of a skydiver, when the skydiver jumps out of the plane and starts falling, the instant the skydiver leaves the plane, her initial velocity in the vertical direction is 0, just like we did in projectile motion, and she experiences very little air resistance. As the skydiver continues to fall, her speed will begin to increase, and she is now accelerating. Okay, as the speed of the skydiver increases, okay, so this is important, as the speed of the skydiver increases, the magnitude of the resistance acting on her also increases, just like your hand stuck out the window. During the time that the air resistance is increasing, the net force on the skydiver is decreasing. So you imagine there's a force of gravity pulling down, and this air resistance that's in the opposite direction of the motion is getting larger and larger and larger. So that means that the acceleration of the skydiver starts to decrease. Eventually, the magnitude of the air resistance becomes great enough that it equals the magnitude of the force of gravity. So if you imagine you have a force, or an object here, force of gravity pulling down, and you have an air resistance that's pointing in the opposite direction, and when those two balance, you end up with an F net of 0. Well, and if you remember from Newton's first law, F net of 0 can be attached to a constant speed. So that maximum constant speed reached by a falling object is called the terminal speed. This is a picture representation of it, a little vector representation. So right at the very beginning, when the skydiver first jumps out of the airplane, that would be this location right here. Okay, so there's an acceleration due to gravity. Okay, there's the force of gravity, and you'll notice that both the red and the orange, okay, and the net force, they're all the same because there's no air resistance yet, because there's no velocity. As the object starts to fall, the velocity increases. Okay, and as the velocity increases, the force of air resistance increases. And you'll notice on this little section here, I'm going to change to yellow. So you have a force of gravity pulling down, you have air resistance resisting the motion pushing up, and so the net force now, if you compare these two net forces, the net force is actually smaller. Okay, so that net force leads to this acceleration. So our acceleration decreases, yet we're still falling downward, we're still increasing in speed. Okay, so the speed has gone up here, which leads to a greater air resistance, which is getting closer to balancing gravity, which means our net force is going down, and eventually we hit this equilibrium point where we're traveling at a certain velocity. Okay, the air resistance and the force of gravity are balanced, and now I'm traveling at a constant velocity, so you'll notice there's no acceleration. Okay, so would the parachute open the instant she jumped out of the plane? Why or why not? Well, if you've ever just stood in your bedroom and thrown a sheet up and tried to make a parachute out of it, you'll notice nothing happens. It just collapses and lands on your head. Okay, for a parachute to open, it needs to have moving air passing into it. It needs to have that air resistance to inflate the parachute. So if you watch the video again or you watch other skydiving videos, you'll notice that normally they have a ripcord or they pull or throw a little parachute, and that little parachute gets the big parachute to come out, and because they're moving quick enough, the big parachute inflates. Okay, so why does the parachute open? Because there's air particles hitting that larger surface, and then that's where it inflates and then it starts to do its job. What happens after the parachute opens? Now, this is a good physics question. Okay, so if we look at this one here, to slow down, the skydiver must increase the force of air resistance acting on her body. So to do this, the skydiver must increase her cross-sectional area moving through the air. Okay, and you'll also notice that when people skydive, they have certain positions. Normally they're lying on their stomach, and they have their arms and their legs out. That's to increase their overall surface area. If they want to go at a different rate downward, they'll pull their arms in, you'll see wingsuits, you'll see lots of different things. So as soon as the parachute opens though, the upward force of the air resistance is much greater in magnitude than the downward force of gravity. So you have more, if you imagine, here's F of G, and here's a really big air resistance. Okay, so when you look at that, the F net on that object, the F net might be upward. Now that doesn't mean the object is going to move upward, it just means that the force acting on the object is in the opposite direction of motion, which means that object is going to slow down. Okay, so since the speed of the skydiver is decreasing now, the force of air resistance acting on the skydiver also decreases. This is that feedback loop we're talking about. And eventually the air resistance decreases to the point where its magnitude again equals the force of gravity. So now the skydiver is moving at a much slower terminal speed than before, and she can land safely on the ground. Okay, so when you jump out, there's a terminal speed you'll hit without having a parachute. Once you open your parachute, after everything balances out, you'll have a new terminal speed, which is hopefully slow enough that you can land on the ground and not break your legs. This is another representation if you want to just pause it and read it. It was just one thing we came up with in class one day, and it has a few more symbols in it. It's just another way of viewing the same problem. We haven't spent a lot of time on this, but just to make sure I've officially talked about it, the difference between mass and weight. So mass and weight they're used interchangeably a lot in our everyday language, but they have very different meanings. Mass is, the best way to describe it is the quantity of matter in an object. Okay, the only way to change the mass of an object is to either add or remove matter. Okay, that's a little bit simple, but for what we need, it'll work. Okay, so the mass of an object does not change due to its location or changes in gravitational field strength or anything. Okay, so the units of mass are kilograms. And if we're talking about weight, weight is a measure of the force of gravity. So weight is a force, mass is not. It's a fundamental unit. So since weight and the force of gravity are the same since weight and the force of gravity are the same quantity, the weight of an object depends on location and the magnitude of Earth's gravitational field strength at the location. Now this might surprise you, but the strength of the Earth's gravitational field is not the same in all locations. So weight is a vector, its magnitude is measured in newtons. We can do that with a spring scale or a force sensor or a regular bathroom scale. When measuring weight with a force sensor or a spring scale, the object must either be at rest or moving at a constant velocity while being supported by that scale or sensor. Okay, and the reason being, otherwise we would not have F net equals 0 and we wouldn't get an accurate reading. Okay, so we'll spend more time on this in grade 12, but gravitational field strength. Okay, so the Earth has this field, and we imagine fields with little arrows, and we'll talk more about that when we get to the electricity unit. But right here on the surface, let's say right here, let's do it right here, it's easier. We have an acceleration of 9.8 meters per second squared. Okay, well, if you go off farther away from Earth, you might find it's less. Okay, and again, we'll spend more time in grade 12 talking about that, but the effect of gravity is not constant. We use a constant number of 9.8 because we tend to take all of the values on the surface of the Earth as being about the same. Okay, so down here though, if you were to somehow climb to the top of Mount Everest, you'd see that the gravitational field strength is actually 9.7. Okay, so that's a little different than the 9.81 we normally use. To represent this field strength, you can take your original F equals mg equation. If you rearrange it so that g is on its own, okay, you would end up with a force over mass, which is a newtons per kilogram. Okay, so that was how we would measure the field strength. We would say it's a certain amount of newtons per kilogram. So if we increase the amount of kilograms, we can get the new force that's applied to it. Conveniently though, if you look at newtons per kilogram, so this is this right here, there's newtons per kilogram. By the time you cancel the kilograms, oh, look what you get. You get the acceleration on Earth that we generally use in most of our questions. Okay. Force of gravity around the world. This is a little diagram. I believe it's taken from your textbook in this section 4.1, and it's just a way to see that different locations have different gravitational effects. Okay, some of that's due to density, some of it's due to distance from the equator. It's bigger than we need to talk about right now, but just so you understand that that force of gravity, that acceleration due to gravity, is not constant every single place on the planet, and there is some variation. Okay, so something on a ramp. We're not going to do a lot of these problems in grade 11, but we should at least have a little conversation about where some of the values come from. So if we have a 5 kilogram cart and it's on an inclined plane at an angle of 25 degrees, okay, we can ignore friction for this example. So if we put something on this ramp and we let it go, it's going to slide down the ramp. So let's start with what is the normal force acting on the cart? Well, normal is right there. Okay, so to do this, we have to do a little bit of geometry, okay? And what we'll find, if we do some triangle work, okay, and there is a triangle. Let's see, I'll change colors. I'm going to draw this triangle right here. So if that's 25, this is 90, then this becomes 65 up here. Okay, this angle up here, we could move that green line up. It would look like that. If this is 65 inside, then this angle in here is 25 degrees. So this 25 here shows up inside that triangle. Now that's kind of messy, so I'm just going to get rid of that for now, and we'll draw it again in a little bit cleaner version. So that 25 degrees is right there. Okay, and if you need to, draw that yourself, prove it to yourself, and try and connect it. Now, FG is the hypotenuse of this triangle, so it has to be the biggest value. The components can't be bigger than it. So if we have 5 kilograms, okay, and I want the FG here, so FG would be mass times gravity, which would be 5 times 9.8, which would be 49 newtons. Now if I want to find this component right here, okay, and that component there is going to be what balances the normal force. So I need to find that component of gravity. So let's call that FGY just for argument's sake. Okay, so if I want to find that, that would be FGY equals FG times cos 25 degrees. Okay, so we would have 49 times cos 25, which would equal 44.4 newtons. Okay, so the normal force here, if this is 44.4 newtons, if this object is not jumping off of the ramp, then the normal force would also have to be 44.4 newtons. Okay. What is the acceleration of the cart? Well, the acceleration of the cart is going to depend on this vector here because it's the one that's unbalanced and it's going to help move that object down the ramp. So I might call that FGX just for discussion purposes. Okay, so now to get FGX, I would have to do FG sine 25. Okay, and that would be, for the interest of space, I'm going to go 49 times 25 sine, and I would have 20.7 newtons. Okay, and that would be the force acting on the box to the right, bringing it down the ramp. Now if I want to figure out the acceleration, now I go back to my F net, and I'm going to do this in the x direction, so I'm just going to put a little x in there. And the only applied force acting on the object in that direction, so my axis is kind of on an angle. This is my x, and this is my y. Okay, so then I could replace this with mass times acceleration. FGX is 20.7. Mass was 5 kilograms. So 5a equals 20.7. So the acceleration equals 4.1 meters per second squared down the ramp. Okay, so hopefully you can see that there's nothing there that's really beyond your ability. It does take some getting used to. Okay, so getting things on an angle, but again, that's going back to our 2D motion stuff and getting that trigonometry comfortable. Oops, I moved some things around. Let's jump down here. The bathroom scale problem. A 60 kilogram person is standing on a bathroom scale calibrated in newtons. A friend pushes down on the person with a force of 72 newtons. What is the reading on the scale? So one thing we need to establish is a bathroom scale generally reads the normal force. Okay, so when someone's pushing down, or if we use a scale under someone's bottom or something to try and figure out what their effect is on the ground, we're going to try and read that normal force. It's like inserting a sensor in between a person and an object to sort of see what the force of their contact is. Okay, so if we have our person here standing on the bathroom scale and they have a certain FG, okay, so their FG would be 60 times 9.8. Okay, so 60 times 9.8 is 588 newtons, but someone's also pushing down on them with 72 newtons. Okay, so the bathroom scale, and I'm going to use purple for the bathroom scale, the bathroom scale is going to represent our normal force. Okay, and it's what has to push in the opposite direction, so this is balanced because they're standing on this scale. Now here's where we talked about F net and F normal are not the same. Okay, so I'm going to say up is positive. So my normal minus my gravity minus the person pushing. Okay, so F net equals F n, my normal, and then 588 and 72 together is 660. Now if the person's standing on the bathroom scale and they're not moving, what is their acceleration? You're right, it's 0. Okay, so because they're not moving, A equals 0, so the F net is 0. Okay, which means when I solve for the normal force, or what reading would be on the scale, the bathroom scale would say 660 newtons. Okay? Okay, so we have a couple of questions here. These are right out of your textbook. So what I'm going to do in the interest of time is I'm going to make a separate video where I'll answer these 4 questions. And I'll leave you with these, section 4.1, 2, 3, 5, and 7, something to try. Thanks for your time.